Something strange is happening at Mount Etna. And no, the strange part isn't simply that one of Europe's most active volcanoes is erupting. Etna has erupted many times before. Scientists expect activity from Etna. They monitor it constantly. They watch its earthquakes. They measure changes in the ground. They track gases, heat, lava, and activity around its summit. So when Etna starts producing lava and ash, that alone isn't necessarily a surprise. But this time, something about the behavior started becoming much harder to ignore. The ash didn't simply appear and disappear. The activity persisted, and the consequences kept growing. Flights were disrupted. Catania Airport, one of Sicily's major transport hubs, faced repeated closures as volcanic ash remained a problem for aviation. And according to recent reports, the disruption became the longest such episode since 2002. So the real question isn't, why did Etna erupt? The more interesting question is, why did this episode keep going the way it did? Because when scientists monitor a volcano this closely, they're not just watching for an eruption, they're watching for changes in its behavior. And Etna just gave them something important to watch. The volcano that never really sits still. Mount Etna rises above eastern Sicily. It is enormous, active, and complicated. For centuries, people living around the mountain have watched lava pour from its summit and flanks. But modern scientists have something those earlier observers never had: a huge network of instruments. Seismic stations can detect earthquakes and vibrations beneath the volcano. Other instruments measure whether the ground is swelling, sinking, or shifting. Scientists can analyze volcanic gases. Satellites can watch changes in heat from space. Cameras can continuously observe the summit, and field teams can go directly into areas where conditions allow them to collect observations. All of these systems are trying to answer one basic question: what is Etna doing right now? And just as importantly, what might it do next? That's where things become complicated. Because a volcano isn't a machine with a simple on and off switch. It can change, it can speed up, it can slow down. Different vents can behave differently. Lava can emerge in one location, while explosive activity occurs somewhere else. And activity can sometimes decrease almost as quickly as it begins. That is exactly why scientists don't look at one signal and immediately declare what the volcano will do. They look for patterns. And that's where this story gets interesting. The first clue. During 2026, Etna had already been showing plenty of activity. In June, researchers documented changes around the Voragine Crater, including a developing fracture system and lava emerging from a vent on the mountain's eastern side. By late June, lava was flowing from the area. Then activity continued into July. A new fissure developed between the Voragine and northeast craters, producing explosive activity, lava, and ash. At one stage, the volcanic cloud rose several kilometers above the summit. And then something important happened. The activity didn't simply follow one clean, predictable storyline. It changed. Some activity intensified. Some weakened. Some stopped. Other activity continued elsewhere. In early July, the explosive and effusive activity along the fissure gradually declined and then stopped almost suddenly. But Etna wasn't finished. Gas emissions and other activity continued around the summit craters. This is the first thing to understand about Etna. An eruption isn't always one single event with one beginning and one ending. It can be a sequence. One vent becomes active, another changes. Lava moves through one pathway. Gas escapes through another, and the mountain's behavior can shift as the pressure and magma pathways beneath it change. But then came another development, and this one would affect something far beyond the volcano itself. The ash that wouldn't go away. Volcanic ash might look harmless from a distance. The cloud of gray material drifting through the sky can even look beautiful. But to aviation, volcanic ash is a serious problem. That's because aircraft cannot simply treat an ash cloud like an ordinary weather cloud. When ash enters the atmosphere around an airport, authorities have to consider where that ash is going, how concentrated it is, and how conditions are changing. And Etna's recent activity created exactly that problem. In August, persistent ash emissions from the volcano repeatedly affected Catania Airport. Incoming flights were suspended, flights were canceled, others were diverted, and the disruption continued through the peak summer travel period. That is where this event became much bigger than a volcano story. Because now, Etna wasn't just changing the landscape around its summit, its activity was affecting a major transportation system. And the strange part was the persistence. The ash problem didn't simply vanish after one dramatic burst. It kept returning. And that raises a question. Why? What scientists would normally want to see? Imagine you're monitoring Etna. You see increased volcanic activity. Your instruments begin showing changes. You watch the lava. You watch the ash. You monitor the earthquakes and the gases. Then you observe the activity change. At that point, you want the different signals to tell a coherent story. You want to understand whether magma is rising. You want to know whether pressure is increasing. You want to know whether activity is moving toward another vent. And you want to know whether the current episode is intensifying, weakening, or simply changing form. But here's the problem. Volcanoes don't always behave like a perfectly organized sequence, and Etna is particularly complex. The mountain has multiple summit craters and a complicated network of fractures and magma pathways. Recent scientific work has even highlighted just how different the underground mechanisms behind separate Etna eruptions can be. Researchers studying historic eruptions found evidence that carbon dioxide in water could play very different roles in driving eruptions through Etna's underground plumbing system. In other words, even the same volcano doesn't necessarily use exactly the same underground process every time. And that matters, because if the underground system is complicated, the surface behavior can be complicated too. Expected behavior. Verse. What actually happened? So, let's simplify the mystery. Scientists observe volcanic activity. They expect the signals to change in ways that help explain what the volcano is doing. Activity rises, then it weakens, ash decreases, the eruption changes. Eventually, the episode settles down. Now, that's a simplified picture. But Etna doesn't have to follow it perfectly. And in this episode, the important observation was the persistence of ash producing activity in its real-world effects. The eruption wasn't simply a dramatic moment that happened and disappeared. The ash problem continued long enough to repeatedly disrupt aviation, and that persistence is what made the situation so significant. Catania Airport was repeatedly affected, with authorities extending closures as ash emissions continued. Reports described the disruption as the worst in roughly 2 decades, while the latest coverage said the closure had lasted for several consecutive days during the peak holiday period. Think about what that means. A volcano can be hundreds or thousands of meters above a city, yet something happening at its summit can affect people hundreds of kilometers away. That's the power of volcanic ash. And it's also why monitoring matters. But what is happening underneath? Now we reach the part we can't directly see. Beneath Etna is a complicated volcanic plumbing system. Think of it like a giant underground network. Magma can move through different pathways. Gases can separate from magma. Pressure can change. Rock can fracture. And existing cracks can provide new routes for magma to travel. But here's something important. Scientists cannot simply look at an eruption from the outside and say with absolute certainty, this exact thing is happening 10 kilometers underground. Instead, they combine evidence. Earthquakes provide clues. Ground deformation provides clues. Gas measurements provide clues. Lava chemistry provides clues. Satellite observations provide clues. And when those clues line up, scientists can build stronger explanations. But when they don't line up perfectly, uncertainty remains. That's not a failure of science. It's the reality of studying something hidden beneath a mountain. And Etna is a perfect example. Recent research has shown that its magma plumbing can involve different processes during different eruptions. So when Etna behaves unexpectedly, scientists aren't necessarily looking for one magical explanation. They're looking for evidence. And then there's the second clue. Here's where the story becomes even more interesting. The unusual activity wasn't happening in isolation. Etna had already shown complex behavior during the weeks leading up to the current episode. Earlier in the summer, researchers observed lava flows, explosive activity, new fissures, ash emissions, and changes around different summit craters. At one point, activity along the fissure between Voragine and the northeast crater produced lava and ash. Then that activity declined, but other activity continued. And later, ash emissions again became a major issue. This is important because it changes the way we think about the eruption. Instead of imagining Etna erupts, Etna stops, the reality is much closer to activity changes. Different vents respond, signals shift, activity weakens, another phase develops. That doesn't mean every new change is dangerous. It doesn't mean a catastrophe is coming. And it definitely doesn't mean scientists have discovered some guaranteed prediction of a massive eruption. It means something much simpler. Etna is dynamic, and scientists have to keep watching it. The bigger pattern. Now, put all the pieces together. First, there was activity around the summit and fractures, then lava emerged, then explosive activity developed, then a new fissure became active, then ash rose high into the atmosphere, then some activity decreased and stopped, but the volcano continued producing other signals. And later, persistent ash emissions created repeated problems for aviation. Each individual observation tells only part of the story, but together they show something important about volcanic monitoring. Scientists aren't simply waiting for Etna to explode, they're watching how the volcano changes from one state to another. That distinction is huge, because the most useful information isn't always, is Etna erupting? Sometimes, the more useful question is, how is Etna erupting? Where is the activity happening? How long is it lasting? How much ash is being produced? What are the seismic signals doing? Are the gases changing? Is the ground deforming? Is the activity moving? Are multiple signals pointing in the same direction? Those questions help scientists understand whether an observed change is part of normal activity or something that deserves closer attention. What this does not mean, and this is where we need to slow down, because an unusual volcanic event can easily become exaggerated online. Etna being active does not automatically mean a catastrophic eruption is coming. Persistent ash does not automatically mean the volcano is about to produce some unprecedented event. A surprising change in activity does not mean scientists have lost control of the situation. In fact, monitoring exists precisely because volcanoes can be complicated. The point isn't to predict every single movement perfectly. The point is to collect enough information to recognize important changes as early as possible, and that is why aviation authorities care about ash. That's why scientists care about seismic signals. That's why satellites watch thermal activity. And that's why monitoring continues, even when the volcano appears quieter. A volcano doesn't need to be at its most dramatic to be scientifically important. Sometimes the subtle changes matter more. So, what did Etna actually do? Now we can finally return to the title. What did Etna do that scientists didn't expect? The answer isn't that Etna suddenly performed some impossible geological trick. The more interesting story is that its activity developed into a persistent and complicated episode, with ash emissions continuing long enough to create repeated and unusually prolonged disruption. The volcano showed that its activity couldn't be reduced to one simple eruption moment. It shifted between different forms of activity. Lava appeared. Explosive activity developed. Ash emissions changed. Some activity stopped. Other activity continued. And later, persistent ash became a major issue for aviation. That is the unexpected part worth paying attention to. Not because the scientists were completely blindsided, but because Etna demonstrated once again that monitoring an active volcano is about tracking a constantly changing system. And that's a much more interesting story than simply saying, Etna erupted. What scientists are watching now? So what happens next? Scientists continue watching the same kinds of signals they've been watching all along. Earthquakes, ground deformation, gas emissions, thermal activity, ash, lava, and changes around Etna's different craters and fissures. They're looking for patterns. If activity decreases, that tells them something. If it suddenly increases, that tells them something else. If ash emissions persist, that's another signal. And if several independent measurements begin changing together, that could become even more significant. This is why volcano monitoring is less about one dramatic image and more about thousands of small observations. A camera captures something, a seismic station records something, a satellite detects heat, a field team examines a new fracture, a gas sensor measures another change. Then scientists compare everything. Piece by piece, they build a picture of what the volcano is doing, and sometimes they picture changes. The real lesson from Etna. There's a reason Etna continues to fascinate scientists. It's not simply because it is large. It's not simply because it erupts frequently. It's because it gives researchers a chance to observe volcanic processes again and again. Every eruption adds another piece to the puzzle, and every unusual behavior raises another question. Could magma be moving through a different pathway? Could gas be playing a larger role? Could the activity be shifting between different parts of the volcanic system? Or could several processes be happening at once? Scientists may not have a single answer to every question immediately. And that's okay, because the purpose of monitoring isn't to pretend that every event is perfectly predictable. It's to reduce uncertainty, to understand what changed, to identify what matters, and to recognize when a volcano starts behaving differently. The final question, and that's the unsettling thing about watching Etna. Scientists don't need to predict every eruption perfectly. They need to recognize when the volcano changes its behavior. Because the most important warning isn't always a giant explosion. Sometimes it's a pattern, a signal that lasts longer than expected, an area that starts behaving differently, a new pathway, a change in gases, a shift in seismic activity, or ash that simply refuses to become yesterday's problem. And that's what makes Etna so fascinating. Even after centuries of eruptions, the mountain can still surprise the people watching it, not necessarily by doing something impossible, but by reminding us that beneath the surface, the system is still moving, still changing, still revealing new clues, and scientists are watching every one of them. Because sometimes the warning isn't that a volcano is erupting, it's that the volcano has started behaving differently. And if you want to follow what scientists discover the next time Etna changes the pattern, subscribe. Because the next clue may not come from the crater. It could come from somewhere much deeper,